All right, welcome to my lesson on rhombi and squares. In this lesson, we want to be able to recognize and apply the properties of rhombi and squares. And we also want to know if we're given a quadrilateral, can we prove, is it a rectangle or a rhombus or a square? Let's start out with some new vocabulary. A rhombus, we've been studying parallelograms in this chapter. So now we're going to study a specific type of a parallelogram known as a rhombus. Rhombus is a parallelogram with 4 congruent sides. And we're also going to talk about squares. A square is a parallelogram with 4 congruent sides and 4 right angles. Now you're probably saying, hold on, is a square a rhombus? Yes, a square is a rhombus because it's a parallelogram with 4 congruent sides. But is a square also a rectangle? As we're going to learn later on, square is also a rectangle because it's a parallelogram with 4 right angles. So a square is a very unique and interesting shape in that it falls into both of these categories. It's a rhombus and a rectangle. So what other properties do we know about rhombuses? Here's some important things to recognize. If a parallelogram is a rhombus, then its diagonals are perpendicular. Okay. Now this isn't true of all parallelograms. We do know in all parallelograms that the diagonals bisect each other, but it's only when your parallelogram is a rhombus, where all 4 sides are congruent, that these diagonals come into the relationship where we have right angles formed. You can picture if we were to extend these sides out, we could make a parallelogram that is no longer a rhombus, because these sides are much longer than the other sides. And if you draw the diagonals in this parallelogram, you can see how the angle at which they intersect is clearly not a 90-degree angle. It's only once we get to be a rhombus that we can count on those diagonals being perpendicular to one another. Now, another thing we know about a rhombus is that each diagonal that you draw will bisect the pair of opposite angles. We know in parallelograms that opposite angles are congruent to one another. But it's only in a rhombus that each of these angles is bisected, cut into 2 congruent angles. Okay, let's see what we can do with that. Could we, first of all, before we proceed, could we get comfortable with this idea, knowing that these diagonals are going to be perpendicular in a rhombus? If we know that ABCD is a rhombus, I'm just going to mark what we know. Could we prove that AC is in fact perpendicular to BD? Well, when you look at this, you can see that we have these angles that are being bisected. We know if this is a rhombus, that this angle is congruent to that angle. Okay? And now I'm hunting for congruent triangles here. I've got these angles are congruent, these sides are congruent. And another thing we know is that these angles are going to be congruent to one another. And these angles are going to be congruent to one another. So now I could say that these 2 triangles are congruent to one another by angle, side, angle. Congruent to angle, side, angle. If these 2 triangles are congruent, then these remaining angles here must be congruent to one another. And if they're congruent to one another, then we could say if this one is x, then that one is x. If they're congruent to one another, and this forms a straight line, then we can say that 2x equals 180 degrees. And therefore, each of those angles must be 90 degrees. So that's how we can prove that in a rhombus, the diagonals are going to be perpendicular to each other. Here we've got a problem where the diagonals of this rhombus intersect at point V. And if the measure of an angle WZX is 39.5 degrees, I'll just label that, could we find the measure of angle ZYX? this whole angle right here. Could we find that angle? Well, what do we know about rhombuses that's going to help us work our way around to get to these angles here? If it's a rhombus, then these angles are congruent to one another. So these are all 39.5 degrees. And we know that these angles are congruent to one another. Let's call those x. Okay? If we can find 2x, then we've got this angle that we're after. If these angles are x, we also know that these angles here are x. Okay? And there's a couple different ways you could approach this. You could say this is a quadrilateral, and I know all of these angles are going to add up to 360 degrees. And you can make a nice big long equation and solve for x that way. But you also might want to simplify it and break it down and say, I know it's a rhombus, and therefore the diagonals are going to be perpendicular. Now I've got a right triangle. So this might be simpler. X plus 39.5 degrees must equal 90. Remember, the acute angles in a right triangle are always complementary. So I could subtract 39.5 degrees from both sides of the equation, and I would get x equals 50.5 degrees. Good. But what they want is this whole angle. So what they're looking for is 2x. 2x, the measure of angle ZYX, equals 2x, which in this case would be 101 degrees. Okay, so you can see how all the things that we know about rhombuses really help you crack this puzzle and find the information you're after. Let's try another one. This one involves some algebra. Here are the diagonals of this rhombus intersect at V again, and they tell us that WX is 8x minus 5 and WZ is 6x plus 3. Okay? Well, if this is a rhombus, what do we know? We know all four sides are congruent, and therefore there should be an equation there that jumps out at you. 6x plus 3 must equal 8x minus 5. Okay? And we can solve that for x by subtracting 6x from both sides and adding 5 to both sides at the same time. And we end up with 8 equals 2x. We divide both sides by 2. We get 4 equals x. Okay. Next, we got another rhombus. This time they're telling us that the measure of angle ABC is 126 degrees. I'm going to label that so I know that's that entire angle. Could we find the measure of angle CDB? So this guy right here, they want to know that angle. Okay. Well, if this is a rhombus, what do we know about the diagonals? They bisect these opposite angles. So if this angle is 126 degrees, then each of these two angles must be half of that, 63 degrees. And since the opposite angles are congruent, this is also 126, and these are bisected as well. So each of these angles has to be 63 degrees. All right, here we have another rhombus. This time they're telling us BC is 4x minus 5, and CD is 2x plus 7. Hopefully you recognize this one. If it's a rhombus, we know these sides are going to be congruent to one another, and you should be able to pull out an equation there and find that 2x plus 7 equals 4x minus 5. Okay, we can solve this for x. Subtract 2x from both sides, while we add 5 to both sides. And we end up with 12 equals 2x. And when we divide both sides by 2, we get 6 equals x. Okay. All right, so now let's talk about squares. Throw squares in there as well. This is a great Venn diagram that kind of puts this all in perspective. We've been talking about parallelograms, And now we've introduced this new type of parallelogram, rhombi, where all four sides are congruent. And we talked about in the last lesson, another type of parallelogram, rectangles, where all four of the angles happen to be right angles. And there's this one little spot in our Venn diagram where they overlap, where you can have a parallelogram that is both a rhombus and a rectangle. It has all four sides congruent and all four right angles, and that's our square. So now we can take the converse of those theorems that we looked at for rhombuses, and we can use these to prove what type of parallelogram we have. If the diagonals of our parallelogram are perpendicular, we know that condition only happens in a rhombus. So if we find that condition, we can say that parallelogram must be a rhombus. Another thing we can recognize is if a diagonal bisects a pair of opposite angles, that condition only happens in a rhombus. So if we have this condition, our parallelogram must be a rhombus. And another check that we can look for is if we have a parallelogram with one pair of consecutive congruent sides, we know that must be a rhombus. Because if this is a parallelogram, we already know that the opposite sides are congruent. AB is congruent to CD, and BC is congruent to AD. And there you can clearly see that we have a rhombus. And if we have that condition that we looked at in the Venn diagram, if a quadrilateral is both a rectangle and a rhombus, then we know it's a square. All right, so let's take a look here. Could we do a two-column proof here to prove that this is in fact a rhombus, LMNP? And let's make two columns. We're going to make some statements, and we're going to make some reasons. Okay. And we're going to restate the given information. They're telling us that LMNP is a parallelogram. Okay, that's given. They tell us angle 1 is congruent to angle 2, and angle 2 is congruent to angle 6, also given. And then before we start our proof, we always make sure that all of the given information is marked. So angle 1 is congruent to angle 2. Okay, and then angle 2 is congruent to angle 6. I'm going to mark that as well. And they want us to prove that this is a rhombus. Well, based on those conditions that we looked at, what would be the fastest way to prove that this is a rhombus? I'm thinking 6.18 here tells us if we've got a diagonal that bisects a pair of opposite angles, that's enough to know that it must be a rhombus. We've almost got that condition right here. All we need to do is prove that angle 5 is congruent to angle 6, and we'd be all set. And I think probably the fastest way to do that would be to say, hold on, I know LP is parallel to MN, right? And why do I want to state that? First of all, that is our definition of a parallelogram, right? Don't forget, a rhombus is a type of a parallelogram. And if these sides are parallel, now I could conclude that angle 1 and angle 5 must be congruent. So angle 1 is congruent to angle 5. Okay? The reason is those are alternate interior angles. And we know that when the alternate interior angles are congruent, or when the lines that form these angles are parallel, that the alternate interior angles must be congruent. So it looks like we have enough information to prove that LN bisects angle PLN and angle MNP. Okay, that is our definition of a bisector, because we're recognizing that it's created these two congruent angles. Okay, and then we can go ahead and say that LMNP is a rhombus because we meet that condition. okay, where if a diagonal bisects a pair of opposite angles in a parallelogram, then it is a rhombus. Okay? All right, that's not too bad of a proof, just a couple lines. Let's take a look at another one. Here, do we have enough information to prove that ABCD is a rhombus? They tell us that ABCD is a parallelogram, very important. AD is congruent to DC. Is that enough information to prove that AD, there's a typo there, let's call that ABCD, is a rhombus? Well, if it's a parallelogram, we can go ahead and mark that DC must be congruent to AB and AD must be congruent to BC. Or you might have recognized that it meets this condition that we had here in 6.19, where we just have one pair of consecutive sides in a parallelogram. As long as it's a parallelogram and not some other type of quadrilateral. But if it's a parallelogram and there's one pair of consecutive congruent sides, then you know all four sides must be congruent, and then it must be a rhombus. So yes, we do have enough information there. All right, Hector is measuring the boundary of a new garden. He wants the garden to be square. He has set each of the corner stakes 6 feet apart. So that means all 4 of these stakes are set 6 feet apart. What does Hector need to know to make sure that the garden is square? Okay. Well, he needs to know that each of these angles is going to be 90 degrees. It's the easiest way for him to figure that out on this scale, working with, let's say he has, I don't know, a 20-foot tape measure. Well, what he can do is he can measure these diagonals. And if that diagonal gives the same measurement as this diagonal, then he knows that his parallelogram is not just a rhombus, but it's also a square, because then he knows it's a rectangle. And if you're a parallelogram that is a rhombus and a rectangle, then you must be a square. All right, what else have we got here? We got one more. Oh, a couple more. Dave has a shape he knows to be a parallelogram and all 4 sides are congruent. Which information does he need to know to determine whether it is also a square? Well, what does this mean? He has a shape he knows to be a parallelogram and all 4 sides are congruent. When I see that, I know this shape is a what? It's a rhombus, isn't it? So, what do I need to know to determine if that rhombus is also a square? If we look at choice A, the diagonal bisects a pair of opposite angles. Well, that's true for all rhombuses. So that just confirms for me that it's a rhombus. Doesn't tell me whether or not it's a square. The diagonals bisect each other. Well, that's true in every single parallelogram. All parallelograms have diagonals that bisect each other. If we knew the diagonals were perpendicular, well, that is true for all rhombuses. Again, it just confirms that it's a rhombus. But only if that rhombus is also a rectangle will the diagonals be congruent. So that's what he would need to know to confirm that his rhombus is in fact a square. All right, one more fun problem where we get to do a little bit of graphing here. They want us to determine whether parallelogram ABCD is a rhombus, a rectangle, or a square with these given points. If we plot these points, A at -2, -1, B at -1, 3, C at 3, 2, and D at 2, -2, do we have enough information to figure out whether this is a rhombus, a rectangle, or a square? Well, first of all, is it a parallelogram? Because if it's not a parallelogram, it isn't any of these. So what's the fastest way to determine whether or not this is a parallelogram? could we take a look at the slopes of these opposite sides? If these slopes are equal, we know the lines are parallel. And then we could take a look at these lines as well. So if we look at this line right here, we go from A to D. We go down 1 unit and over 4. So I know my slope here, M, equals down 1 over 4, negative 1/4. Let's take a look at B. To go from B to C, I go down 1 over 4. So I know the slope here is also negative 1 over 4. So I'm just going to go ahead and mark those parallel. Those are parallel. Here, going from A to B, I go up 4 over 1. Up 4 over 1 is a slope of 4. And likewise, going from D to C, I go up 4 over 1. So here we have a slope of 4. Okay, so these segments are also parallel. We definitely have a parallelogram. Now, is this parallelogram a rhombus? Well, you may have noticed that every single one of these sides had the same delta y and delta x. And we can plug that in our distance formula. Distance equals the square root of our change in x squared plus our change in y squared. So we know every single one of these sides is going to have the same square root of 1 squared plus 4 squared. Every side is going to equal the square root of 17. That means all 4 sides are congruent. Therefore, it's not just any old parallelogram, it's a rhombus. But could it also be a rectangle? And if it was a rectangle, wouldn't that necessarily mean that it must be a square? What's the fastest way to determine whether or not this is a rectangle? There's 2 ways you could do this. You could take a look at the slopes of these lines. The slope of this line segment is negative 1/4. The slope of this line segment is 4. And that tells me these 2 slopes are negative reciprocals of one another. And if 2 lines have slopes that are negative reciprocals, I know they're perpendicular. That means that's a right angle. And you may recall from our first lesson on parallelograms that if you have a parallelogram with 1 right angle, then you have 4 right angles. So, is this also a rectangle? Yes, it is. And if it's a rectangle and a rhombus, it must be a square. Now, there is another way you could check to see if this is a rectangle. You could do the distance formula right here. And you could compare it to the distance formula right here on this diagonal. If those diagonals are congruent, then you definitely have a rectangle. Let's do that real quick. Here, I'm going to say the distance from A to C is the square root of, my change in x going from A to C is 1, 2, 3, 4, 5 units. I come over here, so that's 5 squared. And my change in y is 3 units. 5 squared plus 3 squared. I'm not even going to crank that out. I'm just going to go straight to the distance from B to D and check it really quickly. If I go from B to D, my change in x is 1, 2, 3 units. And my change in y is 1, 2, 3, 4, 5 units. So already you can see that these are going to be the same distance. This is going to be the square root of 25 plus 9, which is the square root of 34. And this is also going to be the square root of 34. So 2 different ways there to determine whether or not this is a rectangle. If you've already done the work to get the slopes, why not just take that shortcut and use that method? Well, I hope you've enjoyed this lesson on rhombi and squares. Go ahead and smash that like button and let me know if you have any questions. Thank you.